Hey guys, welcome to this first video in a series of several about magnetism. It is the same as what would be covered in a first year engineering calculus-based physics course. In this first video, we're going to cover some of the basics about the magnetic field, namely its shape and its direction. In addition, we'll take a look at magnetic materials, try to classify them, and then take a closer look at why certain materials might be magnetic while others might not. Let's get started. Before continuing on with this video, I highly recommend visiting the vet.colorado.edu website and taking a look at the Magnets and Electromagnets lab simulation. The simulation will help you visualize and construct a magnetic field, which will make much more sense during this explanation if you've seen the simulation first. So first here we examine a bar magnet. Now most of us have had the opportunity to play with these before, and some of the things that you probably noticed about them is that if you have two of these magnets, the like poles of the magnets, that's what we call the north and the south ends of the magnets, the like poles repel one another, but the opposite poles attract. Now what's very interesting about a bar magnet is that if you take a bunch of compass instruments and you place them around the bar magnet, you will see that the needles of the compass align along the magnetic field lines. So here I have an image showing that. Now in the PhET simulation that I referenced earlier on in the video, you were able to kind of take a look at that and see how even inside the bar magnet there appeared to be magnetic field lines. By visualizing this, it becomes very apparent that the lines of a magnetic field bar magnets always form closed lines. Now by convention, the field direction is taken to be outward from the north pole and into the south pole of the magnet. But that's just a convention. There really is no beginning or end to these bar magnets. Now this will become a very important concept when we get closer to studying Maxwell's equations. But we have quite a long way before we get to that. Now, as can be visualized with the magnetic field lines, the magnetic field is strongest inside the magnetic material. This is where the line density is the most, or the lines are closest together. The strongest external magnetic fields are near the poles. A magnetic north pole will attract the south pole of another magnet and repel a north pole, as we said. Now before we get into more information about the material that makes up magnets, let's think about the Earth's magnetic field, something that we probably learned about from a very early age. The Earth's magnetic field is actually crucial and fundamental to sustaining life on our planet because it provides a shield that deflects cosmic rays and other harmful radiation from reaching us. What's also very interesting about the Earth's magnetic field is that we use it for direction. Now we say that the north end of a compass will attract to the north pole, but it's really only the geographic north pole, because if the opposite poles of magnets interact, then that means that our geographic north pole is in fact actually a magnetic south pole. The magnetic field lines of the Earth enter the Earth near the geographic North Pole. Now you may be thinking, wait, we just said that these field lines conventionally point away from north, but keep in mind that the geographic North Pole is the magnetic South Pole, so the field lines should appear to terminate on that, but in fact they pass right through the core and the mantle of the Earth. Let's now dissect magnetic material. We can start this by chopping a bar magnet in half. Now before I give you the outcome of what will happen, I want you to pause the video and think about what do you believe should happen to the two pieces of magnetic material that previously made up the bar magnet before it was cut in half. It turns out that no matter how many times you cut a bar magnet in half, it will always form a dipole. In other words, one end of the new piece will always be north and the other end will always be south. This will happen all the way down to the electrons that make up this material. The kind of magnetic material falls into one of 5 categories. Ferromagnetic material, not to be confused with ferrimagnetic materials, are materials that have smaller groups of atoms that have banded together into areas called domains, in which all the electrons have the same magnetic orientation. That's why you can magnetize them. Electrons are teeny tiny magnets, basically. They have a north and a south pole, and they spin around an axis. This spinning results in a very tiny but extremely significant magnetic field. Every electron has one of 2 possible orientations for its axis. In most materials, atoms are arranged in such a way that the magnetic orientation of one electron cancels out the orientation of another. Iron and other ferromagnetic substances, though, are different. Their atomic makeup is such that smaller groups of atoms cluster together into these areas called domains, in which all the electrons have the same magnetic orientation. Now, before ferromagnetic material has become magnetized, the domains point in every which way. But as they're exposed to other permanent magnetic material, the domains begin to orient themselves in the same direction, and this then produces a permanent magnetic material. A permanent magnet, therefore, is nothing more than a ferromagnetic object in which all the domains are aligned in the same direction. Now, what's really interesting is that there are only 4 elements that are ferromagnetic at room temperature. Now, I say at room temperature because several other elements can also become magnetic at very, very low temperatures. Iron, nickel, cobalt, and gadolinium are those 4 ferromagnetic materials. Now, you might be thinking, well, what about neodymium? I heard that it's the most magnetic and it's used in so many electronics. Well, yes, neodymium is a rare earth metal and it's also somewhat ferromagnetic, but to make a rare earth magnet out of it, it actually has to be made from an alloy of neodymium, iron, and boron to form the actual magnet. Now, at this point in an electromagnetism course, you've already studied all the electro part of electromagnetism, so you know quite a lot about electric fields. So it's actually quite useful to compare and contrast the electric and magnetic fields because very soon they'll become very dependent upon one another. Now, the electric field and electric material can exist as a monopole. In other words, I can have charged material that is only positive or only negative. Now, I can also make an electric dipole, or I can have polar material, but I don't have to. It can exist as a monopole. Magnetic material, on the other hand, has only been found to exist as a dipole. In other words, I can't find a magnet that's just a north magnet or just a south magnet. I always find the magnetic material as a dipole. This is going to become extremely important when we look a little bit at Gauss's law of magnetism and establish some of the foundation for Maxwell's equations. This also leads to a very interesting observation that electric field lines are not continuous. They have an origination point and a termination point, whereas magnetic field lines are continuous and neither start nor end anywhere. Now, before we wrap up this first video on magnetism, let's quickly talk about the magnetic field units. The standard SI unit for the magnetic field is the Tesla. Yep, the same as the car company. Now, a smaller magnetic field unit also exists and is called the Gauss. Yep, the same as Gauss's law. Now, 1 Tesla is equal to 10,000 Gauss. We'll get into some other important units for the magnetic field and take a look at how the Tesla is made up as a compound unit in the next video.